In the next session, we are going to talk about the coordination compounds. They playing very important role in our daily life. For example, the Wilkinson's catalyst. When we talk about the Wilkinson's catalyst, it is nothing but PPH3 triphenyl phosphine tries RHCl. This is a homogeneous catalyst which is used for the hydrogenation of the alkenes. Then we can talk about the Ziegler-Natta catalyst. We have studied this Ziegler-Natta catalyst many times in the polymer reaction. The Ziegler-Natta catalyst is a complex of titanium chloride with the triethyl, that is C2H5 thrice aluminium, which is a heterogeneous catalyst which is used for the polymerization of the alkenes. Then we have another compound called as ferrocene. Ferrocene is the sandwich compound of the iron having the two C2H5 rings. So it will be said like this. So this is the ferrocene compounds having a commercial importance. Then we can talk about vitamin B12. Vitamin B12 is having cobalt, which is the coordinate complex. Then we have hemoglobin, which is having iron, which is a coordinate complex of the iron. Then we have chlorophyll, one of the important for the greenness of the trees, containing the magnesium. They're all important for their different uses. They're all coordinate compounds. Then most important one, cisplatin. Cisplatin is cis platinum diamine dichlorocomplex, which is nothing but the anti-cancer drug. So they're playing very important role in our daily life. So when we talk about the coordination compounds, we should know some of the definite words like coordination entity. Coordination entity, it is something like you will be having a central metal ion which is bonded to some negatively charged ion or the neutral molecules. There is a term ligand. Ligand is the ion or the molecules which are attached to the central metal ion. So in this complex, platinum is attached to the diamine and dichloro complex. So it is something, the amine and the chlorine, these are the ligands. When we talk about the coordination numbers, the number of ligands which are directly bonded to the central metal, we call this coordination number. So now here 2 plus 2, that is total 4. So 4 ligands are being attached to the central metal. So we can call this as coordination number is 4 over here. When we talk about this kind of ligands, the ligands are different type depending on how many donor atom it has. It can be bidentate, monodentate. In case of monodentate, let's say ammonia, this is having only one nitrogen atom to be donor. Then Cl minus, these are all monodentate atom. We can have a bidentate, for example, like NH2, let's say CH2, CH2, NH2. So we have this bidentate, 2 nitrogen atoms are donor over here. When we take such kind of bidentate, tridentate elements, so whenever there is donor atom, it's more than one, we overall call them as polydentate. So whenever you have a polydentate atoms, they form the complexes which are having a cyclic structure. For example, if I use this as a ligand, let's say it is ligating with the copper. Copper has a coordination 4, so we need a 4 nitrogen here. So this is NH2, CH2, CH2, NH2, NH2, CH2, CH2, NH2. So here we can see it has formed a cyclic complex which we call it as the chelating ligands or metal chelates. So the compound which forms such kind of coordinate compound in a cyclic form, they are called, these ligands are called as chelating ligands, and the complexes which are formed are called as metal chelates. With respect to the coordination compounds, how these coordination compounds are formed and all, we have most important theory that's called as the Werner's theory. According to the Werner's theory, every element has two valencies. One is called as primary valency and the second is called as secondary valency. When we talk about the primary valency, we call this as ionizable valency. We are nowadays call this as the oxidation state. While the secondary valency, we call this as non-ionizable valency, which nowadays we call it as coordination number. So every element tends to satisfy both its primary as well as secondary valency. But when we talk about the metal, to about its secondary valency, it's fixed and it's always directed towards a fixed position in the space. So in short, the secondary valencies of the element which determines the stereochemistry of the complexes. Now, in the initial part, we'll be talking about the IUPAC nomenclature of the coordination compounds. When we talk about the IUPAC nomenclature for the coordination compound is a combination of one cation and anion. So, whenever we talk about cation and anion, you have to first identify whether your complex is a cationic complex or whether your complex is the anionic complex. For example, if I have a complex, let's say K4 FeCN6 and another complex of the compound, let's say CO NH3 5 times ONO Cl2. Now if I look at this particular complex, this is a coordination sphere. Outside the coordination sphere there is a metal cation. So metal cation will be having positive charge. So definitely if this is having positive charge, then the complex will be having negative charge. So this particular coordination sphere is the anionic sphere. If I look at this, outside this sphere there are Cl minus ions. So these are minus charge. So definitely the charge on the complex is the positive. So this is cationic complex. And if there is no charge on the complex, we call them as the neutral complexes. So we divide our coordinate complexes into three types: cationic, anionic and the neutral. So before you name your complex, it's very important first of all to categorize it, whether it is cationic or whether it is anionic complex. We have different rules while giving the IUPAC nomenclature to the complexes. First rule, while naming the complex, the name of the cation has to be written first, followed by the name of the anion. Now in case of cation, if your complex is cation, you write the name of the complex first. If your complex is anion, you write your name of the complex later. While naming the coordination sphere, the ligand names, now when we talk about this is something which is related to naming the complex. While naming the complex, the name of the ligand has to be written first, followed by the name of the metal. Now when we talk about naming ligands, we are talking about if we have to name the ligands, then we have a different ligands which are written. For example, when we talk about the fluorine, we can call them as fluoro. Nowadays, however, according to the recent nomenclature, anionic ligands will be end up with the O. In general, if the anion name is end up with the IDE or ITE or ATE, the final E is replaced by the O. So if I talk about the fluorine, we can call this as fluorido. It's fluorine, so we can call this as DO. So it's replaced simply by DO. So it's fluorido. We can call this as fluorido. Cl minus is called as chlorido. Then bromine is called as bromido. Then CO3 2 minus is called as carbonato. So whatever textbook or book you are referring, just refer to the different naming of the ligands. Accordingly, these ligands is to be followed. Generally, when we talk about negative ligands, they end up with the term O. Neutral ligands, they will simply name with the molecules. For example, if I have, let's say CH3NH2, then we can call this as methylamine. And if we have a general positive, say they will end up with the IUM. For example, if you have NO plus, then we call this as nitrosonium. We have NO2 plus, we can call this as nitronium. So accordingly, we can select the name of the ligand. The ligands in the complex are named in the alphabetical order, whether they are negative, neutral, positive, without the separation by the hyphens. When more than one ligand is present, then we can use the prefixes such as di or tri. But if you have a chelating ligands, then we have to use the prefixes like bis, tris, tetrakis, like this. So when the complex is anion, the name of the central metal, if this is only for the anionic complexes, that should end up with the term ATE. When you're writing the name of the metal, it should be followed by the oxidation state of the central metal, that has to be written in the Roman number. So in case of nomenclature, all these rules has to be followed. We'll definitely follow these rules, or we'll see how to utilize this particular rules when we are solving the MCQ related to this. But we have to follow this particular rules while solving the while doing the IUPAC nomenclature of this. In the next part, we are going to talk about the isomerism related to the isomerism part of the coordination complexes. Now this isomerism has been divided into two types. One is a structural isomerism and the second one is the stereoisomerism. When we talk about structural, it has been divided into different types. First of all, let us talk about ionization isomerism. In case of ionization, let us talk about example. Let's say cobalt NH3 4 times, Cl2 NO2, and second complex is cobalt NH3 4 times, Cl NO2, and outside the bracket I have only Cl. Now in this case, if we talk about the molecular formula of these two complexes, it is same. But if I dissociate this, I'm going to get the NO2 minus ion. And if I dissociate this in water, I'm going to get the Cl minus ion. So though both are having same molecular formula, but the different types of ions are formed in the solution. So they are ionization isomers of each other. They are also classified as hydrate isomers. For example, if you have Cr H2O, let's say 6 times, we have in the bracket Cl3, then Cr H2O 5 times, Cl2 H2O. Now when we talk about these two particular complexes, they are having different positions of water molecules. If you look at this, all water molecules are present in the coordination sphere, while here one of the water molecule is outside the coordination sphere. So when this will be dissociated, they will be creating the different number of solvent molecules, and that's why here we are called them as the hydrate isomerism. We can also divide them as the coordination isomerism. What is this coordination? Let's say cobalt is forming the coordination sphere with the ethylene diamine, and chromium is forming with the cyanide. It can be reverse also, like cobalt is forming the coordination sphere with the cyanide and the chromium is forming with the En. Now here the two metals has exchanged their coordination spheres, so we call them as coordination isomers of each other. Also, the fourth type is the linkage. In case of a linkage isomerism, let's say cobalt is complexed with the ammonia 5 times NO2, and this is cobalt NH3 5 times ONO. Now in this two complex, the molecular formula is same, but here the donor atom towards the cobalt is nitrogen, while here the donor atom towards the cobalt is oxygen. So the ligand is same, but the type of the donor atoms acting over here are different. That's why we call them as the linkage isomers. Now in case of the next, we are going to talk about the stereoisomerism. So in stereoisomerism, there are two types of isomerism. One is the geometrical and the second is the optical isomerism. Under geometrical isomerism, this is only possible when the coordination number is 4 or 6. In 4 also, it is only possible for the square planar complexes, not for the tetrahedral, because in tetrahedral complexes, the geometry, the positions are not adjacent for the ligands. So only for the square planar complexes, the geometrical isomerisms are possible. So there are two types, cis and trans. When I talk about the square planar, we have to just understand it's a metal bonded to the 4 ligand. Now this is possible when at least 2 of the ligand are different. So it is possible for M, A2, B2 type for the complexes, or it is possible for M A2 BC complexes, or it is possible for M ABCD. So these four type of ligands, they will show the cis and trans. So always remember there are four positions, 1, 2, 3, 4. So 1, 2 or 2, 3 or 3, 4 or 1, 4, they are adjacent to each other. So when you have two ligands, let's say A is having 1 and 2 positions, then it's cis. But if A is having position 1 and 3, that will be trans in nature. Similarly, when I talk about the coordination number 6, we call them as octahedral complexes. In case of octahedral complexes, if the formulas are like M A3B3 or M A4B2, this kind of complexes can show you the geometrical isomerism. But we need to remember in octahedral complexes, the geometries are like this. And numbering will be done like this. So this is 1, then 2, 3, 4, 5 and then 6. So always remember 1 to 2, 1 to 3 and 1 to 5. Again I am repeating 1 to 2, 1 to 3, 1 to 5. Then 1 to 4 and 1 to 5. They are all cis. But if I talk about 1 to 6, or when I talk about 1 to 6, or when I talk about 2 to 4, or when I talk about 3 to 5, they are all trans to each other. So they are on opposite sides. So it's something like this side is on one side and this side is on one side. So if 1 to 2, 1 to 3, 1 to 4 and 1 to 5, that kind of arrangement is there, then it is cis arrangement. But if I talk about 1 to 6, A is having 1 and 6 position, that kind of ligand we call it as trans arrangement. So this formulas, just we have to remember, this kind of complexes can show us the geometrical isomerism. In case of optical isomerism, for the tetrahedral complexes it's possible, but they are very labile in nature, no one has isolated them. So we have to remember there are some octahedral complexes only which are showing the optical isomerism. Now octahedral complexes with the polydentate ligands, especially the bidentate one. So this kind of ligands can show you the optical isomerism. Or let's say this is having AA twice. The remaining two valencies, if it is satisfied by the same ligand, monodentate ligand, or if it is satisfied by the different ligand also, then these three complexes will show you the optical isomerism. But when I talk about these two complexes, their cis form, they are active, but trans form are optically inactive in nature. While solving the MCQs related to the VBT as well as CFT, one common fundamental we are going to use. Now here we have to decide the type of hybridization. Generally we decide. Now I'm just writing the coordination number here, the type of hybridization that is to be decided on the type of ligand. Now first let us talk about coordination number 4. In coordination number 4, we have two type of hybridization, that is sp3 hybridization. It's giving us the tetrahedral geometry, and there is sp2 dehybridization or dsp2 hybridization, that is giving us the square planar. Now when I talk about sp3 hybridization, we are generally going for the outer gap. It is generally, we have to remember, there are 5 d orbitals, and the metal d orbitals are always degenerate, that is they are having the same energy. When the ligand approaches, on the ligand approach, these 5 d orbital split into two groups. Either they split into 3 and 2 up, or they split 3 up or 2 below. So when 3 are having same energy, it's T2G, triply degenerate. Generally they are dxy, dyz and dxz, and this is EG group, that is dx square minus y square and dz square. Similarly here EG is down and T2G is up. Now this degeneracy will decide that how much gap is created between this. That is totally depend on the type of ligand. If this gap is very large, the electron will prefer to stay in inner shells, and this is inner shells generally prefer the dsp2 or sp3 hybridization. That is because of the strong field ligand. But if it is a weak field ligand, then it generally gives us the sp3 hybrid. If the coordination number 6 is there, it's an octahedral geometry only. That geometry is common, but the hybridization is of two types, sp3 d2 or d2 sp3. Similar thing. If you are using the inner shells, then the ligand is strong filled, and if it is outer, the ligand is the weak filled ligand. So accordingly, we can decide the respective properties of all the complexes. For example, if I have to decide the related to this, for example, we have nickel 4 times 2 minus, and we have nickel Cl4 2 minus. Now, if I have to decide the properties of this, what is the geometry of these two complexes and what is the magnetic nature of these complexes, first I will concentrate on nickel. When I'm talking about the nickel is having atomic number 28. So nickel is 28. So electronic configuration is argon 3d8 4s2. Now here in this case, the nickel is present in +2 state. So if it is +2, these two electrons are lost. So now nickel is having 3d8. So in d orbital, 1, 2, 3, 4, 5, 6, 7, 8 electrons are there. 4s is empty, and even the 4p is empty. Now in this case, we have to think about the cyanide. Cyanide is a strong field ligand. If I talk about the coordination number 4 with the strong field ligand, generally the hybridization preferred is dsp2. If it is dsp2 hybridization, I need one of the d has to be empty. To make it empty, what we'll do, we'll shift this electron inside. So when we'll shift this electron inside, all the electron inside will be paired up. So now this d, one empty, s and 2p will be utilized for the bonding, that is coordinate bond. But the remaining electrons, if you'll find, they are all paired up. That's why I will call this particular complex is diamagnetic in nature, because all the electrons are paired up, as well as since we have decided the hybridization is dsp2, the geometry of this complex is square planar. Similarly, in this case, the configuration of nickel will remain same. But this time the chlorine is weak filled, and if it is weak filled, it is sp3 hybridization. In case of sp3 hybridization, we don't have to affect this particular d orbitals, they will remain as it is. But for the required sp3, they are already empty, so this will be utilized for the bonding. So in this case, we can see the two electrons are unpaired, and that's why this complex is paramagnetic in nature with the geometry tetrahedral. So overall, you can see, you can predict the magnetic property and the geometry of the any complex if you simply use this particular table. So for particular coordination number 4 and 6, we can use this particular table to predict their geometries and their coordination numbers. Now the next part that we'll be talking, that the factors which are determining the value of the splitting. As I told you, the d orbitals are generally degenerate, but when on the approach of ligand, they split into the group. But how much splitting will cause here, that is decided by point number 1, the nature of ligand. As I told you, if we use a strong field ligand, then this particular splitting between the two will be very large. But if you have a weak field ligand, then the splitting will be very small. It is also decided by the oxidation state of that particular metal ion. In general, if the high is the ionic charge on that central metal ion, larger is the value of the splitting, and if that is small, then this delta will also be the small. So these are the factors which are affecting the splitting pattern. The next part, that is, will decide the splitting pattern, that's the geometry of the coordinate entity. Generally it is found that for the tetrahedral complexes, the splitting is about 1/2 of that of the octahedral. So octahedral splitting is more. So we can calculate for the splitting of tetrahedral is 4/9 of that of splitting pattern of the octahedral complexes. It generally about half of the values of the octahedral entities. So here overall these are the factors which are affecting the splitting patterns of the coordinate complexes. Stability of the complexes will also be dependent on certain factors. Stability of complexes will be dependent on more is a basic nature for the ligand. More basic are the strong field ligands. So the stronger basic in nature, more will be the stability of that complexes. For example, if the nickel is forming a coordination complex with ammonia and with ethylene amide, ammonia is more basic, so K, that is stability constant, will be 6.1 into 10 raised to 8, while here K is equals to 4.6 into 10 raised to 18. Now here En is like a twice of donor compared to that particular ammonia. So here, since the donation capacity has increased over here, the complex is becoming more stable. So if you have a chelating ligand, it will give you a more stable complex. In the similar pattern, if I am comparing the ammonia with another compound, let's say we are comparing with the cyanide complexes. So nickel with the cyanide complex and ammonia, it will be more stronger with the cyanide. But if I comparing ammonia with En, it is more stronger with the En because En is forming the chelating ligand. So we have to understand there are different type of the factors which will decide. First of all, in case of monodentate ligand comparison, more basic nature, more is the stability. Second factor, chelating ligand have more stability compared to the non-chelating. So these are the two factors we have to remember while deciding the stability of the complexes.